Okay guys, welcome to another video. Today we're going to be talking about a subtopic in physics known as electrostatics. And a lot of this has to do with like geometry and like finding the total amount of charge enclosed within some geometric boundary. And in this case, we're actually given the charge density of some cylindrical volume. So right there, we're given the charge density as a function of the radius of the cylindrical volume. And if we kind of imagine this over here, um, a cylinder, something like this, with a radius r. Uh, the height of the cylinder is 3. The radius is 2 meters. Okay, right there we could like calculate the volume of the cylinder. We can like calculate the total volume, but really what we're looking for is uh, the charge density. I'm sorry, the total charge in this non-uniformly distributed charge in this volume region. Um, let's see. So basically, what this looks like is 5r squared, and it's in radial coordinates. So I'm just imagining the charge distribution being like something like this, where the region like underneath this and around this axis is like the increasing charge density as it reaches this maximum at the surface of the cylinder. I hope that makes sense. That's how I'm imagining this system. Anyway, uh, engineers care about this type of thing. Like electrical engineers will care about the charge distribution in a region of space because electric fields introduce disturbances to other electrical signals, and they cause electrical currents and voltage drops, and they just interfere with all sorts of other stuff. So engineers have to design around that, and that means that they have to be aware of how the charge is distributed around these volumes. And in this case, we're given just a very simple uh, charge distribution per volume in terms of R as 5r squared millicoulomb per cubic meter. Okay. Typically for static charge density, you will have just rho be a constant and then multiply by the volume, in which case I could do what I said earlier and employ the volume of a cylinder, which I believe is the circumference times the height. So 2 pi RV, right? And then that would give us the total charge inside the cylinder if it was just all uniformly distributed in a homogeneous way. But it's not. It's distributed as described by this 5r squared function. So that's just an interesting thing I think I should point out. So in the case of the non-constant charge density, we have to integrate over the volume. And it's going to be 5r squared dv However, cylindrical coordinates would have it such that dv equals r dr d theta dz. All right, and the z is the height of the cylinder, theta is the angle swept out by the geometry. I'm just going to say angle swept by geo dot. R, obviously the radius, right? And these are the differentials, and then we have this extra factor of R. Do not forget that. Very common mistake I hear. I actually made that mistake before, so do not forget this R. All right, so let's recast this triple integral in terms of our new transformed cylindrical coordinate system, right? So this is just going to be Q equals, I'm going to draw my little sum symbols first, and then I'll do 5r squared, and it was dv, but dv is equal to r dr d theta dz. All right, now let's look at our bounds. Let me just redraw the cylinder again, and we said radius equals 2 and the height is 3. So z goes from 0 to 3. The cylinder includes like the whole thing. It's not just like a fraction of it. If it were, then you would just adjust these bounds accordingly. But in this case, it's just a circle. Also, what is R? It's 2. So starting at the center of the cylinder here, you basically count outwards, right? So it's like the radius increases as you go out. This could be like 1, this would be 2. Hopefully that makes sense. But I see no reason why we cannot just evaluate the integral now and get the total charge of the thing, right? So I'm just going to do this kind of rapidly, but I'm going to go as fast as I can write neatly is what I'm going to do. So really this is 5r cubed, right? So what that means is the integral of 5r cubed is just going to be 5 fourths times r to the 4th dr. Oh wait, I'm sorry. I performed the integral already. I put the bounds here now. And then I can write d theta dz. Continuing on with the integration, now we'll just leave the first one in place and evaluate the second one, which is going to be simply theta evaluated from, well, let's evaluate the previous one first. It gets kind of confusing if you do not. That's going to be 20 multiplied by these two. I'm just going to rip that constant out into the front immediately. And then we just call this d theta dz. This just equals 40 pi. Now we're down to 1 integral, and that equals 120 pi, and that's coulombs. And so really we can say that our Q total is equal to 377 millicoulombs of total charge within that cylinder, in which like electrical engineers might be designing other components, right, that have to be able to withstand those certain electric field strengths depending on where they are located in relation to that charge source. And so that's just some basic electrostatic stuff. I hope that this was helpful. If you like this video, please subscribe to my channel. Also hit the bell notification so that you may be notified the next time that I release a new video. And as always, if you would like me to cover anything specifically, just mention it in the comments, and I would be more than happy to oblige. Thank you for viewing, and I'll see you next time. Have a good one.